So today we're going to really talk, well, on Wednesday we talked about really how we get snow. So those processes of evaporation, of condensation, of those ways that we can grow our droplets or our ice crystals until they become big enough that they fall out. And so really what we're going to look at today is what happens when that has happened. So what effect does snow have on the Earth system and on us as humans, and in particular how our warming temperatures have affected snowfall in different places and how it's predicted to continue to change and what we might have to do to deal with that. So really today's sort of theme is the outlook for snow. As a reminder, quiz 3 is available this weekend as usual. What is different, and I even underlined it and put it in red so hopefully everyone will remember, is that I'm going to close the quiz slightly earlier on Monday, and that's because I would like you to be able to see what you got right or wrong in time to sort of go over it before the midterm. Does that make sense? So I do want you to be able to see what you got right or wrong. So don't get caught out. It will close at 11 a.m. Okay? So with that being said, let's actually talk about more interesting things, which is what effect does snow have? Once it's on the ground, once we've got it out of the sky and onto the ground, what sort of effect does snow have on the Earth system? And the first and the most obvious one is, it's really white. And so it's really going to dramatically affect Earth's albedo. Why might it not actually matter as much as we might think in the winter? Why might the albedo of, say, that particular area that is snow covered, why might it not matter as much in the winter months? Yes? Yeah, absolutely. We're tilted away from the sun. So if you're at the North Pole in the winter months, in the middle of winter, you don't get any sunlight. So it doesn't really matter how reflective the ground is, right? Because there's no incoming light to begin with. So absolutely, the fact that that's of the winter hemisphere, it's not getting as much of that incoming sun's energy to begin with, means it doesn't have as big an effect as if it was in the summer. And that's why we're most concerned about the melting of our summer sea ice, because that does have a big effect on our albedo. Okay, so most snowfall actually occurs outside the high Arctic and the center of Antarctica. And remember, we had the very smart guy on Friday, or Wednesday rather, that told us exactly why. And that's because we need a certain amount of moisture in our atmosphere before we can form clouds, before we can form these big enough snow crystals. And so it's just too cold and too dry there for that to happen. And so that's sort of our pattern of snow on the ground. And it's pretty important for our ecosystems, the fact that we have this, because snow is actually an insulator. Does everyone know that if you're stuck in a mountain somewhere and the sun goes down and you can't escape, then you dig yourself a snow hole, right? You sort of dig a hole and you crawl inside. And that's because snow has lots of air pockets in it. It's a really good insulator. So if you think about sort of the ground has been receiving that energy from the sun all summer, it's absorbed a certain amount of that energy. We also just have a certain amount of energy escaping out of the center of the Earth because of radioactive decay in our mantle. And so the Earth is emitting heat. If we have this nice thick layer of fluffy snow with lots of air pockets in it, that heat gets trapped in those air pockets, and so it keeps the ground sort of warmer than it would otherwise be. Because above the snow, it might be like minus 20 degrees Celsius. With that insulating snow cover, if it's deep enough, we can keep our temperatures pretty close to or even above freezing at the very base of our snow. And that's obviously pretty important for animals and vegetation. Vegetation doesn't like to be frozen solid. It doesn't behave very well if you freeze it. And so it really, that snow cover in sort of deep snow cover in our mountains really protects that underlying vegetation from the most extreme temperatures that winter can throw at it. Also, we have little burrowing animals that can quite happily exist because it's ever so slightly warmer down there. It's closer to the freezing point and it's not as cold as above. Things like that snow cover will also affect non-ecosystem related stuff. So things like if we have a snow cover above our sea ice, or if we have snow cover on our glacier, then it means that that also is protected from perhaps more melting in the early spring. So snow cover and duration of that cover is pretty important. Does that make sense? Yep. So let's think about life. Life has made some pretty amazing adaptations to existing in the snow. Can anyone think of something that a plant or an animal does that means it's specially adapted to snowy conditions?
Bears.
What do bears do?
Hibernate.
They hibernate, absolutely. So perhaps something might hibernate. They might find themselves a cave or a sort of a snow hole and hibernate. What else? Come on, I know it's Friday, but you guys can think. What color are the bears up in the Arctic? White. So do you know that some animals actually change the color of their coats? So things like snow hares, they might be brown during the summer and change to be white in the winter. That's going to be a problem for them if it isn't white in the winter anymore. They're going to really stand out. So that's something that they do. Everyone's being very silent today. I'm going to get you talking eventually. So here are some things that life can do. So we have special fungi and bacteria that actually can live in the snow. They're especially adapted to do that. Have you ever noticed the shape of trees? In these really mountainous regions, they tend to look like that. And they have branches that bend down. A lot of your Christmas trees have branches that will bend downwards. And that's to deal with the weight of that snow and that ice. But snow is really heavy. If you've ever had to shovel it, it weighs a lot. It's basically just water. And so in those sort of high regions, if your branches sort of bend down a bit, then that ice and snow can slide off. Whereas if you're something more like our deciduous trees outside, then they won't be adapted. Their branches would perhaps break under that stress. So that's really cool. We even have animals that can produce special enzymes and chemicals that prevent them from freezing. And I think this is really neat. And I have a little video to show you that this is the case. I'm not making it up. So here we have a little frog that doesn't hibernate. Well, he does hibernate by just sort of stopping functioning. But he is completely frozen solid. Okay? But when spring comes around, if we allow the sort of time to move forward, there he is in the middle. He's gradually thawing out along with the ground. He wakes up a bit and he hops off. So, and it's really amazing what he does. He actually pumps sugar into his cells. And in high enough concentrations, that sugar actually prevents those cells from bursting. It basically acts as a natural antifreeze. And that level of sugar in our cells would kill us. And in the winter, as the spring comes round and he wakes up a bit, he has this mechanism to get rid of that sugar and allow him to function again. So it's really neat, and you can sort of read a bit more in that video. We've talked about coats that thicken. If you're a snow hare, then you have big feet to travel on top of the snow, for example. And also things like the patterns of life, the hibernation. Maybe you migrate to deal with this sort of existence. So life is amazing. It's come up with these ways of living with snow cover. So what happens to snow? So we have snow on the ground, and it can sublimate. So remember, that's that process where it doesn't melt first. It just goes straight from a solid to a gas. And so that can happen. It can also just melt when temperatures rise at the end of your winter. But some snow might not melt. And if that snow sticks around for more than 1 year, in fact for sort of several years or decades, then it can build up and form ice. And that's really the process where we sort of build our glaciers and our big ice sheets. It all started from these little individual snowflakes. And so let's look at the snow that hangs around, because that's how we define our snow line. If you've heard of the term the snow line, it's really the line across our mountain that marks the point where above that, last year's sort of winter snowfall hangs around through the whole summer. There's basically snow above that point for the whole of the year. Below that snow line, the winter snow melts away during summer. So you can see our beautiful mountains. I think this is from New Zealand, with the snow line running through there. Okay. And so that elevation varies year on year. So it's a very good indication of what our climate is doing. Because first of all, the temperature of the summers controls how much melting there is. So a warmer summer might melt more, and so you get a higher snow line. The more snowfall you have will affect how much of that, sort of, if it melts away fast in the summer. And so these are sensitive indicators of climate change. So what do you think latitude will do to my snow lines? So if, say, we go from our latitude, maybe like 30 degrees north or so, up towards the pole, do you think our snow lines are going to get higher, or do you think they're going to get lower? Lower. Why? Because it's colder, absolutely. This isn't really advanced stuff. So as we go towards the poles, our temperatures are colder, and so snow can exist further and further down our mountains throughout the summer. But how about increasing distance inland? How about that one? How might distance inland affect the altitude of your snow line? Stunned silence. It's the quietest time in the room is when I ask a question. What were we saying affects things like how much snow sort of the center of Siberia got compared to, say, the east coast of the US? Moisture, absolutely. So what do you think might happen to, say, our snowfall amounts from perhaps closer to the coast to further inland? Are we going to have more snow at the coast or more snow inland? At the coast. So what will that do to our snow line? Is our snow line going to be higher at the coast or lower at the coast? Lower, absolutely. And it's to do with that amount. If I get 10 centimeters of snow and 1.5 meters of snow, then if we have the same temperatures, then those things will melt at the same amount. And I can melt 10 centimeters here, and I'll be at ground, and there'd be nothing left. But I'd still have 1.33 meters or something where we had the high amount of snowfall. And so that's how that affects our snow line. So, if temperatures were the same in mountains in Colorado and in mountains in California, where would the highest snow lines be? Any more? I think there's a few empty seats today. Right, let's take a look. So there's a 70-30 split for Colorado, and they would be right, the Colorado people. They would be the highest snow lines. And I think thinking about this in terms of just talking about it can be a bit of a challenge. So I want to show you, because I want to convince people of this. There we go. So I want to show you an easier way of thinking of this. I'm going to talk today about the power of diagrams. Because a lot of people come to see me and they have beautiful pages of neat notes, but there's not one diagram in there. And a lot of Earth system science is about diagrams. So if I have one mountain, two mountains, I have a high snow line and a low snow line. Which of these mountains is it warmer at? The left one or the right one? Left. Which of these would get more snowfall? The left or the right? Right, okay? It becomes much easier to visualize this when you have this in front of you. In an exam, what I love to see if I'm looking through is someone's drawn me an orbit and they've like drawn the Earth and which way it's tilting. I like to see this. People are thinking and they're drawing these things, okay? So diagrams are really powerful. When you're studying this weekend, try drawing a couple because it makes so much sense in it. You could write a page to explain the same thing you can get done in a diagram. So that's my advice for studying this weekend. Right, so yes, indeed, Colorado would have the highest snow lines. So how is snow actually measured? Because really, the snow is falling in pretty remote areas. And we measure different things. We can measure the snow depth. So that's obviously quite important. We can measure the snow extent, which is basically just over what area does that snow fall. And SWE stands for snow water equivalent. And that's basically saying, for whatever depth of snow it is, how much water is actually in that depth. Okay? And really what we mainly do today is monitor this by satellites. And so we can use things like microwaves are emitted from different surfaces in different ways. And so with satellites moving across the top, we can measure the changes in that. And also the snow just looks whiter. Okay? But those do have to be tested. They can't necessarily always tell us everything about it, because it's pretty difficult to get at exactly how much water is there or how deep that snow is. And so we have to send people out, and they do. They wander off in their snowshoes and their skis off into the mountains once a month to I think about 180 or 280 locations along California, and they measure it. They measure the depth, and they weigh it. And there's a cool little video here that shows you a sort of a slightly more advanced way that we can do this in some places now, and they're called SNOTEL stations. So let's have a quick look at our little video.
And while that might be good for skiers, what does this really mean? It's actually all about water management, especially out in the western U.S. We're here along the Continental Divide at one of the over 700 SNOTEL stations. These stations are placed remotely in the western U.S. and Alaska at high elevation areas to provide scientists with up-to-the-hour data on snow, water, and weather conditions. You might wonder if all of these stations are so remote, how do they get the data up to a central area once an hour? The answer is not what you may think. The SNOTEL communication system is based on meteor burst technology. What does that mean? Meteors, when they enter the atmosphere, they burn up around 25 miles up and leave an ionized trail. The radio on top of this tower sends a signal about 25 miles up into the atmosphere, where it bounces off the remains of meteors and down to a ground station where they collect the data. So now that we know how the data transmits back to humans and computers, how is it measured here remotely in the middle of the mountains? This nondescript white area behind me houses a pillow with an antifreeze liquid in it. And when the snow accumulates on top of that pillow, it pushes some of that liquid out. Scientists measure it, and now we know what the snow water equivalent of the snow really is. Now, while all of this automation is great, it's not foolproof, and sometimes there are inconsistencies in the data. When that happens, scientists actually throw on a pair of skis, have to physically come up here, take a core sample, weigh that core sample, and determine by hand what the snow water equivalent really is. And while this might not seem as fun as measuring snow to find your next powder day, this is really the backbone for water management in the western U.S. So the next time you're hanging out in the backcountry and you come across a hodgepodge of radio towers and this wind chime looking thing, there's a good chance that it's a SNOTEL site.
So there you go, SNOTEL sites. So if you're ever wandering around up in the Sierras, then if you come across these, this is how we monitor our snow and why we care, why we put all of this technology and effort and money into doing this is because it's so important for our water resources, as he said there. Because snow in mountain regions, not just in the US, but around the world, contributes to water supplies for over 1 billion people. So we do want to know what's up there. And it's especially important for us in the western US. We get a lot of our water from snowmelt. And the nice thing about snow is it basically acts as a natural reservoir. We build reservoirs to trap water so we can take it out when we want it. Well, that's basically what the snowpack does in the mountains of the Sierra Nevada, is that snow falls in the winter when we're not really growing anything, when it's not that hot, and we don't necessarily need all that water. And it isn't until our temperatures rise, perhaps in the late spring or early summer, when our plants are starting to grow, when our agriculture is getting going, that's when the water comes down. And so it acts as like a natural reservoir system. It traps the water when we don't need it, and it releases it in those really important spring and summer months when we do. Okay? So it's really very important. And so that melting snow flows into streams, but also importantly, as it gradually melts, it also seeps into the ground. And it replenishes that groundwater that we've mentioned a couple of times. So all that water that's contained in the little spaces in our soil and our rock. And we are using that sort of to make up the difference right now in California. And we're using it much more quickly than it's being replaced. And so the fact that we have snow melt that does that is really important also. Not only that, but we also have hydroelectric power generation all along our Pacific coast. And what that does is it takes that water and it uses that sort of the gravity basically that's moving that water downhill, and it uses that water to turn turbines and generate electricity. So we also need our water for that. So let's look a little bit more carefully about snow water equivalent, and you get to do some math, which I know you're all excited about. So why do we care about snow water equivalent? Why can't we just measure the depth and be done with it? And it's because the density of snow can be so different. Do you remember we talked about all of those different shapes of the snowflakes and how they can be different sizes, and then if you're getting that snowfall in different sort of wind conditions, then what we can have is we can have sort of new snow with a density of maybe 5%, or maybe when it's closer to that sort of 0 degrees Celsius, we can have a density of 20%. And that's a really significant difference to the amount of water that we're going to get as that melts away. So that's why we use snow water equivalent. And this is basically what that means. It says if we have 36 inches, I'm being kind, it's in inches, so 3 feet of snow, if that snow has a density of 10%, so 10% of it is water and 90% of it is air, then when that melts, what that will give us is sort of a layer of water maybe 3.6 inches thick. Okay? So, everyone's favorite thing, what would the snow water equivalent be of the block of snow that's 48 inches and it has a density of 20%? So think about it for a second. Talk to your neighbor. Should be able to do this in your head. We got any more votes to make? If you haven't voted? Right. So let's see how good our maths is today. Oh, well done, guys. Excellent. So yes, 9.6 inches. And you know the easiest way of doing it is saying, what's 10% of 48? It's 4.8 times 2 is 9.6. So that would be our snow water equivalent. It would be 9.6 inches. Okay? And that's the information that water managers need in California in order to sort of predict how much of our supply we'll have and say how much we might need from groundwater, how much we might need from our reservoirs. So what's happening to our snow? Unsurprisingly, as we've been getting hotter, we have been losing our snow cover. Okay? So it's a relatively gradual change. It's been declining by maybe 1.3% per decade, and that's especially in the northern hemisphere. What this graph doesn't show you is that if you look at the spring and the summer months in particular, then they're much more dramatic losses. Okay? And it's one of those funny things that it's a bit patchy again, because it depends quite a lot on local conditions. So yes, the overall pattern means that increasing temperatures will reduce the amount of snow, but some areas are decreasing much more rapidly, and some even might be increasing in the amount of snow that they see. And so I want to get you into groups of 2 or 3, because no one's answering any of my questions today. And I want you to think about looking at this map. So first of all, like orientate yourself, work out where the US is, work out where Asia is, work out where Europe is. So where are the largest decreases in snow cover? These different colors predict what percentage of our snow we'll have by 2080 to 2100 following one of our particular RCPs. Okay? So where are the largest decreases and why are they occurring there? Does snow cover decrease everywhere? If not, why? And what are some of the implications? Think about what this might mean for some of the people and also the ecosystems. So the TAs are around, so they'll stand up, wander around, I'll wander around. So 2 or 3 minutes to think about this. Right, so I spoke to the people at the back and they had some brilliant answers for me. So where are the largest decreases happening? Europe, definitely. Where else? West Coast, that's right where we are. So those red colors, and how much is that snowpack potentially decreasing by? 75 to 98%, 3/4 to nearly all of that snowpack might be lost. And this is one of the higher of those RCPs or those scenarios. But that's still a pretty worrying thing, right? That's not really what our mountains, it's a big drastic change. What about elsewhere? Does snow cover decrease everywhere? Where does it grow? Closer to the poles. Why might we be limited in the amount of snowfall we get close to the poles? Can you remember why? Moisture, absolutely, because there's limited moisture. As we warm up the planet, what do you think might happen to the amount of water vapor in our atmosphere? It's increasing. And so what we might see is that in those areas right around the edge, basically at our lower latitudes, rising temperatures are probably going to melt away a lot of that snowfall. And also we might get much more of that snowfall happening as rain instead of as snow. But in our really cold areas, that even when we warm up the planet, are still pretty cold and probably below 0 degrees Celsius, then that increase in moisture in the atmosphere means that actually we might get more snowfall in some of these places. So I think that's really interesting, those high Arctic. So that's sort of a nice little summary there, and you guys definitely have this, which is great. But what are some of the consequences of that? How might that affect people? Who owns 2 large pieces of wood that they bring out every winter? No one knows skis? Yeah? Skiing, okay? If you like skiing and you like going up to the mountains and skiing in Big Bear or whatever, make the most of it, okay? Snowboarding as well. There's actually a whole bunch of things. So let's first of all talk about our ecosystems, because we are Earth system science after all. Does anyone know what this cute little guy is? Does someone say it over here? Begins with a P. Pika, absolutely, it's a pika. And these little things are native to our mountains, and they're not doing so well because these guys live really high up. And in winter, they survive by using that thickness of the snowpack, and it keeps the ground level warmer, and so they're able to move around, and they sort of survive that way. But the problem is if we're decreasing the snow depths, they're much more likely to be exposed to these really cold temperatures that sometimes happen in our winters. And so these guys are not doing so well, these poor little guys. Things like our soils. Our soils are much more likely to freeze. That's going to do damage to roots, to vegetation. It's going to change things like the cycling of nutrients, water and gases. Definitely reduce water availability. If we don't have as much water that's melting in the spring and summer, then that's going to limit the amount of water that's available for, say, vegetation. And from a selfish point of view, that also limits the amount of water that prevents things like our big fires that happen up in the mountains as well. So decreased snow depths will affect both plants, vegetation, and us. We also have potentially less duration of snow cover. It might be more patchy, or it might melt earlier in the season. And what does that mean? Well, for plants, that might mean a good thing. It might mean that they're exposed to sunlight earlier on, and so they have a longer growing season. But they still might be, at the end of the winter, they might be still exposed to really cold temperatures occasionally. We get earlier timing of the peak snow melt. And so all of that water that comes off in the sort of peak sort of melting time in the spring is going to be earlier. And things like fish sometimes rely on their breeding cycle and have lined that up with our peak snowmelt. Also, we get more rapid increases in soil temperatures, especially if we've frozen them. And other things are things like the changes in the density of that snowpack. So if we're going to have more frequent thaws, so more frequent days when that temperature rises above 0 degrees Celsius and then refreezes again, what that does is it creates really hard, icy layers in our snowpack. And that's a really big problem, actually, for our little reindeer here, because they actually dig through that snowpack and they use their sort of hooves to like smash through, and they graze on what's underneath. And so they don't do particularly well in years where there's big, thick snowfalls. But also, as we get these really solid, icy layers, then they can't smash through those, and they can't get through those to get to the vegetation underneath. And you can see the decline that has happened recently between 1961 and 2004, just how much of a difference in population we've seen. And really, they looked at all of the different factors that might be causing it. And for once, it's not predation by us or whatever else. It really is the fact that we're getting these more frequent thawing and refreezing events, and it limits their food supply. So it's a big deal for both our reindeer, but also little burrowing creatures that need to move through the snowpack. And it also reduces the insulating ability as well, because it stops those little air pockets, melts them away. But all of these changes that are happening, it will depend on where you are and on what your ecosystem does and how it usually functions to how well it will adapt to these changes. And I wanted to make the point that all of these changes will affect the structure of the existing ecosystem, not only the different animals and plants that are there, but also the cycling of nutrients, water, and gases. And so it's a pretty complex system. And we're interested to see how this might change. So people, and skiers and snowboarders in particular, it's not good news for the ski industry and our mountain snow resorts. And really, I think I remember saying to you guys that in terms of industries that are sort of lobbying government for action on climate change and carbon emissions, then this is one of the most visible and vocal of our industries, because obviously they can see the end. It's not a pretty picture for our resorts. So this graph shows you how reliable snow will be, so natural snow will be. Under current conditions, maybe 80–90% of the time, we have natural snow, and our resorts in the Alps in Europe are able to sort of operate. And you can see the difference then. If we get 1 degree warmer, we lose sort of another sort of 10% or so. 2 degrees warmer, we're down to maybe 60% of the time we'll have natural snow. By the time we get to 4 degrees warmer, we're maybe 25–30% of the time we'll have that natural snow. And especially for the lower resorts, that really does spell the end for them. And so one solution, one that we've seen a lot around here, is our natural snowmaking, our sort of fake snow, basically, these snow blowers. And I'll post a couple of videos to the Facebook group about how they do this and some of the issues. What do you think are some of the problems of using these things? If you're a resort and you rely on natural snow, why might you not want to have to shift to these things?
It's more expensive.
It's more expensive, absolutely, because you're having to use energy. What else do we need to put into these things in order to get fake snow or ice? Water, absolutely. And in these areas which are potentially going to be more and more water stressed, if we're not getting that nice snowpack or if we're decreasing precipitation, then there's a big fight then about how much of our water we should be using to sort of create this sort of fake snow. So it's really interesting questions to be answered. Other things that will affect us are things like transportation. In most of the US and in Europe, snow is seen as a bad thing because we are not particularly good at dealing with it. We crash our cars into other cars, our airports shut down, things like that. But in areas which are used to snow, then they actually use it quite often. If you're a gas company or a mining company in the Arctic around Canada, there aren't a lot of roads. And so a lot of these companies will stockpile their stuff during the summer, and then when all of the lakes and rivers freeze over, they'll drive their sort of big sort of trucks to collect the stuff. So no one's ever seen ice road truckers? A couple of people, yeah. Ice road truckers. No one ever admits to it either, but yeah, that's what they do, right? And it's a pretty dangerous job if your ice is going to get thinner and thinner and thinner. And they're already seeing that the number of days that they can actually use these ice roads is being cut by 20, 30 days each year. That's significant for them. Things like changes to the traditional way of life for mountain communities and also Arctic communities. They're used to this snow, they're adapted to deal with this snow. Their way of life depends on it. And so if we're seeing changes in the amount and the timing, then that can really affect them. And most importantly for us, water. So we keep coming back to this idea because it is so important. So 75 to 85% of our water supply in the western US, so not just California, but also Colorado, Utah, Arizona, that comes from snowmelt. So we're going to see potentially a change from instead of getting snow in the winter, we might get more rainfall. And that rainfall doesn't sit nicely up in the mountains, it will flow out, okay? And then we also will see, therefore, a change in the pattern of when that water is coming down through rivers and streams. And potentially less replenishing of groundwater, because the nice thing about snow is it melts really gradually. And so that water can sort of trickle down into the ground. But you know, if you've ever walked through Aldrich Park, when they put the sprinklers on, there's only so much water that sinks into the grass, right? And then it just becomes puddles or it runs off. And that's the same thing in the mountains. If you get enough rain, then a certain amount of it will go into the soil, but it really quickly becomes saturated, and then it just runs off. And so we are expecting changes in our water supply as a result of this. And in particular, in California, it's a really interesting thing to think about, because enormous amounts of our water in California is moved. I think we've affected something like 90% of the natural rivers and streams and in some way. And why? Because we have enormous agricultural areas that previously just don't get the sort of water supply that would make them viable. And so, for example, we see now situations where the Colorado River no longer reaches the sea because of the amount of water that we and also a number of other states and Mexico take out of it. So we have our network of aqueducts, and you can see that the Los Angeles aqueduct that runs up through the Eastern Sierra especially depends on that winter snowmelt. Okay? And let's think about where that water goes. So some people are surprised by this. 80% of the water in California is actually used for agriculture. It's not used for people. That sort of, we produce in California over half of the US grown fruit, vegetables, and nuts. Isn't that amazing? So that Central Valley is enormous, and it produces an awful lot of this stuff. And 1 out of every 6 jobs in California is tied in some way to that agricultural system. So it's a pretty important industry, and it's something that we obviously need to make sure that they have water. Urban areas use 20%, but our population is expected to grow by a further 10 million people or so by 2050. That's not necessarily just population growth, but also migration. And then we have our indirect users, our hydroelectric generation, and 15% of our energy supply in 2007 at least was generated by this hydroelectric supply. But that really does differ each year depending on how much rainfall we get. And so it's difficult to build that into our big networking or our big system of electrical energy if we don't know how much we're going to get each year. And so I have a question for you. If we are going to be limited in terms of our water resources in the future, who do you think should have priority? Because we have agriculture, and they use an awful lot of it, but they generate a lot of jobs, they generate a lot of our income for California. We have our urban areas, the 20% that we use. We're not necessarily that efficient. Maybe half of the stuff that we use in Orange County as people goes on landscaping. Is that something that we necessarily should have priority for? And then lastly, a good chunk of California's water actually is deliberately left to keep or maintain the environmental conditions. So for example, in the Delta, they need to preserve a certain amount of water there. So my question for you is, and there isn't necessarily a right or wrong answer, who do you think should have priority access? Few more seconds. Right, let's see what people think. So don't pack up yet, I've got 2 more minutes. So not many people think that we should be a priority. I think you might change your mind next time you can't shower, but of course it's a stupid question really, because we can't treat it that simply. It's not a simple question. And so this is something that you're going to spend time in discussion next week. We're going to look, don't pack up, sit still. We're going to look at how much water is available and who you think should get priority in what aspects. And so I wanted to show you something because this is, I think, a really telling satellite image that was published by NASA last week. And it shows the difference between January the 13th, 2013 and January the 13th, 2014. And that white stuff in that image, some of it is cloud off there, but a lot of that is snow. That is how much snow we currently have in California. We're about a fifth of what we should be at this time. And we have no prospect of big storms in the next couple of weeks. And so this is why we declared a drought emergency last week. That's why Governor Brown said, oi, stop it, we should pay attention, please sort of monitor what you're using in terms of water, don't take extra long showers, things like that. It's a problem. And so just before you go, this is sort of a little bit more of a summary. We just looked at one map for one particular scenario for how water might change and how our snowpack might change in the future. This shows you more specifically what might happen to our snow water equivalent for those different decades. And so it shows you how important that might be for different states around here. So you can have a quick look through that. Okay, I will see you guys on Monday.